Greetings and welcome to the demonstration titled Demonstrating Light Path Operation with the Ocata Digital Twin in Multiband Optical Networks. This work was completed at UPC Barcelona under the Horizon Europe Season project. Digital twins, like Ocata, are high-fidelity virtual replicas of physical systems. Ocata Ndt is a DNN-based digital twin of optical networks to model the propagation of a light path in the time domain. With it, we are able to use DNN models to estimate the QOT of the light path before it is established, and then fine-tune them using real-world telemetry data to better follow the behavior of the light path under operation. In addition, Ocata manages the impairments introduced when using multiband transmission, like interchannel simulated Raman scattering, and recreate the behavior of linear noise and nonlinear noise in the digital twin. Ocata Ndt uses pre-trained models from a model database to build light path configurations. Each light path element is taken from the model database and concatenated to build the complete light path model. The models in the model database are trained using the features that are extracted from the symbols around each constellation point. The FEX block is in charge of extracting these features. The Ocata Ndt then estimates the QOT of the proposed light path and checks to see if it satisfies the QOT threshold of the related modulation format. The QOT estimation block is used to compute the probability of symbols falling outside of detection areas for different constellation points. The QOT of a light path can be represented as a pre-FEC BER. If the QOT threshold is satisfied, it will inform the SDN controller who establishes the light path. The model is then saved to the model database. The NLI mitigation block optimizes the detection area for each constellation point with the aim of reducing the pre-FEC BER and mitigating the NLI effect on the light path caused by its propagation through the fiber alongside other channels. In this figure, you can see the optimized detection area for a constellation point where the red shaded area represents the probability of being outside of the detection area for a constellation point. After applying NLI mitigation, this area is greatly reduced. The model tuning block is responsible for the fine-tuning of each light path model. This is important as there are two main sources of error for QOT estimation. The first, span length mismatch, and the second, different channel than reference channels. The model tuning block monitors for deviation between predicted and actual performance of the light path. Model tuning is performed using actual telemetry data stored in the telemetry database and collected after the establishment of the light path. Fine-tuning the model can help detect abnormal behavior and predict and mitigate the anomaly before light path performance is affected. The virtual testbed for this demonstration was implemented at UPC Barcelona premises. The client has an API with Ocata which acts as the SDN controller and sends a request to Ocata. The telemetry database, which contains time series data, uses InfluxDB. The model database, which contains the pre-trained models, uses MongoDB. Ocata is originally implemented in Python and it is containerized using Docker. The first phase of the demo is to establish a light path where the client, acting as SDN controller, sends a request to Ocata to establish the light path. Here you can see the interactive dashboard that we developed for Ocata Ndt. In the model database, you can see the set of pre-trained models for each span and related reference channel, one in C-band, channel 154, and one in L-band, channel 225. The span models will be concatenated by Ocata to develop one single model for the proposed light path. A request is made from node A to node B that requires 100G service. The requested channel is number 166, which is in C-band. And the number of spans through the light path is 4 spans with a total length of 280 kilometers. The related wavelength for channel index 166 is 1550 nanometers. By clicking on Establish, we can make our request to Ocata, who will provide an estimate of the QOT if applicable. The computed pre-FEC BER is shown here. Let us see the effect of activating NLI mitigation for establishing a light path with similar characteristics. By applying NLI mitigation, we are trying to optimize the detection area for each constellation point, which reduces the pre-FEC BER. Here you can see the pre-FEC BER after applying the NLI mitigation is lower than previously. In this phase, we will see the effect of model tuning using telemetry data collected from an already established light path to update the DNN models of a light path. The ID of the light path is entered to identify which model should be fine-tuned using the collected telemetry data. Ocata retrieves the telemetry data from the telemetry database and uses it to fine-tune the light path model. The new QOT is displayed and can be seen that the pre-FEC BER is lower and closer to the actual after the fine-tuning process. At the end of the light path lifecycle, it must be removed from the network. By passing the ID of the light path to this box and pressing the delete button, we can remove the light path and its related concatenated DNN model from the model database and the digital twin. Thank you for your attention. If you have any questions, please feel free to contact us by email.